Welcome to Mahalearning. In Mahalearning, today we're going to look into a chapter in physics. Physics is a subject which is applied to every single object around us, starting from automobiles, gadgets and the day-to-day usage we do. And we also need to know how this is being applied. But when we learn a theory-wise, when you're looking into a textbook, all we could know is sentence by sentence, and theoretical knowledge is what we earn. But if we could take it to the practical level, it will be useful for every student, not just for the mark's sake, but for their future studies as well. That is what is happening in Mahalearning. Every chapter in physics is being taught why and where it has to be applied. So let's look into today's lesson.
Hi students, physics is an interesting subject. We are going to see our learning components of physics in 12th CBSE. As we discussed, we have 4 learning components: class session, ebook, virtual lab, test and assessment series. As you know, there are 10 chapters and we are going to deal today about the 4th chapter, electromagnetic induction and alternating current. As you know, this is a very large lesson which has many subtopics in it. 25 subtopics are there, 22 subtopics in electromagnetic induction and 3 more subtopics in alternating current. We are going to see the sample of 2 subtopics here.
Today, we should study the phenomenon of electromagnetic induction. If we have a steady current, and the steady current is associated with the magnetic field. But now we are going to look at the reverse process. Can magnetic fields produce currents? So let us understand the meaning of what is magnetic flux. So let it be represented by symbol phi. Suppose we have a surface, and this is the direction of magnetic field, normal to the area, and this is theta. Now I am going to define magnetic flux d phi, passing through an elemental area. Let me call this as dA, as product of B and area vector dA, where area vector dA is defined as dA into n cap. The total flux through the entire area will be given by integral B dot dA. Magnetic flux is measured in unit of Weber. The magnetic induction is defined as flux per unit area, so this is Weber per meter square, which is also called as Tesla. So, the SI unit of magnetic induction, also called as flux density, is 1 Tesla, which is 1 Weber per meter square. Michael Faraday performed a series of experiments where he tried to change flux through a given coil. So, let us say we have a coil, and this is connected to a galvanometer, and I move the north pole of the magnet towards the coil. As I move this towards the coil, I find there is a momentary deflection. The experiment is repeated by connecting the galvanometer, but now, moving the magnet away from the coil. Now when this was done, there was again a momentary deflection, but in the opposite direction. We now consider the motion of the north pole towards or away from the coil, and what happened when we introduce a south pole towards the coil is equivalent to a north pole will move away from the coil. So the deflection will be towards the left. Repeat this experiment with south pole being moved away from the coil, and this is equivalent to introducing a north pole. And therefore, there is a momentary deflection towards the right. If these experiments are repeated by keeping the magnet stationary and moving the coil towards or away from the magnet, similar results were obtained. Not only this, Faraday also noticed that the faster you move the magnet towards the coil, the greater is the magnitude of deflection if coil and magnet are moved towards each other. This is also possible. I have a coil galvanometer, and I move this towards each other, or I am moving both away from each other. Now, all these causes a momentary deflection is observed. However, no deflection is observed when both magnet and coil are stationary, or, we find, the magnet and coil are moving in the same direction, with the same speed. Faraday summarized the result of the experiment into two important laws, which is Faraday's laws of electromagnetic induction. The first says that, whenever there is change in the magnetic flux linked with the circuit, an EMF is induced, and lasts as long as change lasts. The second law says that, the magnitude of this induced EMF, say, is proportional to the diameter of change of magnetic flux. So, E is equal to minus d phi by dt. So in your earlier experiments, when we say that magnet was inserted into this coil, which moved towards the coil, the flux through the coil increased. So, this increase in flux induces a current in the coil. Again, when you move the magnet away from the coil, the flux decreases, and a current is induced in the opposite direction. However, if we keep a magnet stationary near a coil, there is no change in the flux linked with it, and therefore there is no induction. Thus, we can conclude that, whenever there is relative motion between magnet and coil, an EMF is induced. The magnitude of this depends on how fast the flux is changing. So, if you pass this magnet in faster, the rate of change of flux increases, and then the galvanometer shows a bigger deflection. Now, this deflection, however, is momentary, and it's loose, as long as the flux is changing through this coil. So, in how many ways can we induce EMF? We have seen that the flux linked with the coil is given by BA cos theta. So, we can change flux through a coil by changing the magnetic field, changing the area of loop, and rotating the coil in a magnetic field. So, if this is the coil and this is the area vector and this the field, then we can change theta by rotating the coil. So rotating a coil in a magnetic field can induce an EMF.
Animated ebook. This is a self-learning tool for the students. In this ebook, we are going to see about introduction or many methods of inducing EMF and also Faraday's law. This ebook will have multimedia content which is self-explanatory, supported by audio-visual.
You are seeing a coil rotated through an angle theta in the anti-clockwise direction with a peripheral velocity of each side of the loop in meters per second. Draw OA parallel to the plane of the coil loop. The vector of this velocity is denoted by AP, that is, the length of the line AP. The line AP is drawn at right angles to the plane of the loop of the coil. AP is also represented by the phasor representation denoted by U, velocity vector. You can resolve AP into two components, AQ and AAR. AQ is perpendicular to the direction of the magnetic flux. AAR is parallel to the direction of the magnetic flux. Since AQ is also horizontal, angle QAO is equal to theta. Hence AQ is equal to AP sin theta is equal to U sin theta. The EMF generated in A is due to the perpendicular component of the velocity, where angle OAP is equal to 90 degrees. EMF generated in one side of loop is equal to B into L into U into sin theta. Here, B is the flux density in Teslas and L is the length of the parallel sides A and B of the loop in meters. EMF generated in both sides of the loop is equal to 2 into B into L into U into sin theta. When theta is equal to 90 degree, EM is equal to 2 into B into L into U sin 90 is equal to 2 into B into L into U volts. The standard form of an alternating voltage is given by E is equal to EM sin theta. A cylindrical coil is connected to a galvanometer. A bar magnet is inserted inside the coil. As the magnet moves down, the magnetic flux linked with the coil increases. This causes an induced EMF and the galvanometer gets a momentary deflection. When the magnet is pulled outside the coil, the magnetic flux linked to the coil decreases. This again causes an induced EMF, but in the opposite direction. Now, the galvanometer deflection is in the opposite direction. When the magnet moves up and down faster, the induced EMF is higher and changes faster. The coil C1 is connected to a battery E through a key S and a rheostat. Coil C2 is connected to a sensitive galvanometer G and kept close to coil C1. When the key S is pressed, the galvanometer shows a sudden momentary deflection. This indicates that a current is induced in coil C2. You will see now how it happens. When the key S is pressed, the current in C1 increases slowly from 0 to reach a certain steady value. When the current changes or increases, the magnetic flux linked with coil C1 also changes or increases. Due to mutual induction between the coils C1 and C2, the magnetic flux linked with the coil C2 also changes or increases. This change in flux causes an induced current in coil C2. When the current reaches a steady value, the flux also reaches a steady value and hence no EMF is induced in the coil C2. The galvanometer now shows no deflection. You will see now what happens when the switch is opened. On releasing switch S, the current in coil C1 slowly decreases from maximum to 0 value. When the current in C1 decreases or changes from maximum to 0 value, the magnetic flux linked with coil C1 and hence in C2 also decreases or changes. This causes an induced current in coil C2. This current causes an opposite deflection in the galvanometer. You have learned that when a coil is subjected to a change in magnetic field, a current is induced in the coil.
Virtual lab. The highlight of virtual lab is you can practice the experiments based on this chapter. Here we are going to take potentiometer based on the EMF, and you can practice as many as time you want from your home PC. The lab simulation will clearly explain you how to do the concept.
Welcome students to the experiment potentiometer internal resistance of a cell system guided lab simulation. The aim of this experiment is to determine the internal resistance of a Lenchi cell using a potentiometer. Implement the circuit as shown in the instructions. Close the circuit by closing the plug keys. Check the circuit using the Check the Circuit button in the table. First you have to find the balancing length for the infinite resistance. Keep the key in the secondary circuit open. Include the high resistance. Press the contact button on the jockey from the wires 1 to 10 successively and note the approximate balancing point. Now exclude the high resistance. Find the correct balancing point. Click on the table button to display the table screen. Enter the calculated balancing length for the infinite resistance in the appropriate slot. Click on the check button. Close the table screen. Close the key in the secondary circuit to include this circuit. Change the resistance in the resistor box to 1 ohm. Include the high resistance. Move the jockey over the potentiometer wires and note the approximate balancing length. Exclude the high resistance. Now find the exact balancing length. Let this length be L centimeters. Open the table screen. Enter the value of the known resistance in the slot provided. Enter this length L in the appropriate slot. Click on the check button. Calculate the internal resistance R using the given formula and enter it in the appropriate slot. Click on the check button. Applying the same procedure, calculate the internal resistance R by changing the known resistance as 2 ohms and 3 ohms. In this screen, we are about to submit our last entry in the table. Click on the check button. Hope this demo was interesting and also enabled you to learn how to determine the internal resistance of a Leckland-G cell using a potentiometer.
Test and assessment series. As you are a board going student, you have to follow strictly the blueprint. All objective and subjective questions are dealt. Self-automation and instant evaluation is our highlight. Once you submit the answer, you will get to know whether it is right or wrong. Even if it is wrong, you will be guided through the right answer as a feedback. By daily practicing the test and assessment, you will get exposed to all type of questions, objective, subjective, problems, derivations related to physics, application oriented questions, all type of questions along with the solutions which will help you to master this chapter from the comforts of your home.
Well friends, today in Maha Learning we've learned a wonderful chapter and we know where we have to apply this and how it is going to be useful in future. Again, I'm going to meet you with a set of lessons so interesting. Until then, this is Carolyn saying take care.